One of the processes we need to learn in our journey to finding all roots of polynomials is long division. So let's just go back a few years and remember what long division is. If you're setting up long division from this division statement, 356 divided by 3, we start with this notation. We know that we're looking for how many times this 3 on the outside is going to fit into this first 3 here. We know that can fit in one time. So we multiply 1 times 3 is 3, and then we subtract. We get 0. They cancel out. And then we bring down. We are now looking for how many times 3 is going to fit into 5. Well, 3 is going to fit into 5 one time. We multiply 1 times 3 is 3. We subtract. And we bring down. We are now looking for how many times 3 is going to fit into 26. We know that 8 times 3 is 24. So we multiply, we subtract. We are out of things to bring down. So this 2 here we call our remainder. This was not an even quotient. 356 is not evenly divisible by 3. The important part to remember about this process is the fitting into the first place, the multiplying, the subtracting, the bringing down. Largely for polynomials, we are going to follow that same process. In regards to vocabulary, the thing we are dividing is called the dividend. The thing we are dividing by is called the divisor. And our answer is called the quotient. Now, we talked about that you could have a remainder at the end. That shows up when you can't fit things in anymore. We're taking all of this vocabulary and transferring it into our polynomial world. When we record our answer, we want to use our quotient remainder notation that we have here. So we're always going to put the quotient, which comes from the top of this representation, plus a remainder over the divisor. Divisor is what you're dividing by. So let's take this through a polynomial example. First, our setup of long division. So we're always going to be looking at that first place again. So our question to ourselves is, what do we have to multiply to x squared on the outside here to match the first term of the inside? Well, my current inside is x to the 4th. I know that x squared times x squared is x to the 4th. So we multiply. But I also know, like, if I'm multiplying the divisor by x squared, I have to distribute that. So I also have to multiply 3x by x squared, getting positive 3x squared, and negative 5 times x squared, getting negative 5x squared. So our multiply is a distribution. So we identified what we needed, we multiplied, now we subtract. And we subtract from our like terms. X to the 4th times x to the 4th goes away, which is a good thing. 4x to the 3rd minus 3x to the 3rd is x to the 3rd. Negative 7x squared minus negative, so that's actually a plus. 5x squared is negative 2x squared. And then we bring down any of the remaining terms. In this case, it's a positive x and a negative 10. We repeat that process as many times as we can. So again, we're looking at the first term of the divisor. We need it to match the first term of our current inside. Well, if we multiply x squared by x, then we have a match. So I'm choosing x. But if I multiply a polynomial by x, I do need to distribute. So x times x squared is x cubed. That's a good thing. X times 3x is positive 3x squared. X times negative 5 is negative 5x. My multiplication's done. Now I subtract. X cubes cancel out. That's good. You always want your first term to cancel out. Then you chose correctly. Negative 2x squared minus 3x squared is negative 5x squared. X minus negative 5x is 6x, and bring down any remaining terms. All right, our first term of the divisor needs to match the first term of the dividend. Our current first term is negative 5x squared. Well, if we multiply x squared by negative 5, our terms match, which means we need to multiply. So negative 5x squared minus 15x plus 25. Subtract those. All right. So I ask myself, what can I multiply to x squared to get 21x? Well, there's an issue. I can't really multiply by anything to get x squared to be an x. Not a polynomial term, at least. So that's when you know you've run into your remainder. So our remainder here is actually a binomial, and it's when you can't answer that question of what can I multiply by. Just means that you're done with your long division process and ready for the final answer. The quotient, which you find in the top of the long division setup, so that is simply this here, quotient, plus the remainder, which we figured out was 21x minus 35, over the divisor, which is the outside, x squared plus 3x minus 5. For a long division problem, this is your complete answer. To review the steps of long division, I've made this list. The thing we haven't talked about yet is placeholders. So if you notice in our last problem, both our dividend and our divisor started at our highest degree of x and counted down from there. For example, our dividend is x to the fourth, x to the third, x squared, x, and then a constant. Our divisor is x squared plus 3x minus 5. All places of x are accounted for in both of those. So we didn't have to worry about this idea of a placeholder. But if you don't use placeholder for missing x powers, your long division quotient will end up being wrong. So that is something we do need to check for at the beginning of our long division during that setup phase. Then we identify what we need to multiply by. We multiply, usually by distributing. Then we subtract, bring down any remaining ones, and we repeat that process as many times as necessary. When we run out of options to multiply by, we record our answer in the quotient plus remainder form, which is the quotient plus a remainder over the divisor. If you need that set up, it's here. Quotient plus remainder over divisor. Anytime you're simply asked to do the long division or just to divide, this is how we want your answer to be. So let's look at an example that requires placeholders. We set up our long division. This time we're using a fraction bar as our divide by symbol. I notice there's no x squared, so that is going to be by placeholder, that x squared. So in the place of x squared, I'm going to put 0x squared. And then our divisor is x plus 1 this time. The process is the same, even though we had to use a placeholder. So we look. We want to match the first term of the outside to the first term of the inside. I know if I multiply x by x squared, we end up with x to the third. And then I need to distribute. Then we subtract and bring down. Okay, so now we are matching x to negative x squared. If I multiply by negative x, I end up with negative x squared. Distributing that negative x, I subtract, resulting in, so I know that I can make my first term match negative 6x by multiplying by negative 6. You multiply, subtract, I have nothing else to bring down, so I'm done. In this case, my remainder is equal to 0. Therefore, my final answer for this one is just going to be the quotient up here. So the question you might have is, how is this long division going to help us? Well, we don't know how to factor every polynomial. It just doesn't work. Just like we couldn't factor every quadratic. We need other methods. Long division is going to help us with that. So how does this relate to the roots and the intercepts we've been talking about? Well, we know that we could solve polynomials by factoring. There's a theorem called the factor theorem telling us that if the remainder of a division statement is equal to 0, then the divisor is a factor of the dividend. And we could actually use the divisor and the quotient to factor that polynomial. If we have an alternate method to factor, it might lead us to roots we couldn't normally find. Well, let's check that out. Looking at this setup, I don't see any need for placeholders. Hopefully at the end of this long division, the remainder is equal to 0. Otherwise, you can't use it to factor. Therefore, we really don't have a method to find all these roots yet, but let's do it and find out. I want x to match x to the third, that is x squared. So x squared times x is x to the third, and subtract. Bring down anything remaining. I want x to match negative 2x squared. I could do that by multiplying by negative 2x. Subtract. Bring down. I want x to match negative 15x. I could do that by multiplying by negative 15. Subtract. I've run out of terms to bring down, so I'm done. That means that my remainder is equal to 0, which is a good thing. Our divisor, x minus 5, is a factored version of this polynomial. So what that means is I could take x cubed minus 7x squared minus 5x plus 75 and factor it as what I was dividing by times my quotient up here. So we started with a polynomial that we didn't know how to factor. We pulled out one factor using our long division, and now all of a sudden we found a root. So we know we should have 3 because the highest degree is 3. We know that one of the roots comes from solving the factor of x minus 5. But if you look at that quotient, it is factorable. You could rewrite this as x minus 5 and factor that quadratic as x minus 5 times x plus 3, resulting in roots or x-intercepts of long division is just the beginning of us being able to find all roots of all polynomials. Now, we do have to tell you what to divide by for now, but we'll get there when you can make that decision on their own. Here you go. Remember that multiplicity counts as 2 roots, so 5 is 2 roots, negative 3 is the other one. Highest degree is 3, that is 3 roots. We are good. So we took a polynomial x to the third minus 7x squared minus 5x plus 75 that we did not know how to factor. We did not know how to find roots without a calculator. We were told that a factor of the polynomial could be x minus 5. We proved that it was because the remainder was equal to 0. And then we were able to break it down so that the quotient was something we were able to work with, that we've learned about before. This process is going to be so important to us. Let's try it out again. They gave us a division statement, and if it is divisible, they asked us to find all roots of the dividend. I am seeing lots of opportunities for placeholders. There's a placeholder in the divisor, which is possible, and there are 2 placeholders in the dividend. We need to multiply by x to the third in order to get 2x to the fifth. I like to line up my quotient with its like terms, and when I multiply, I line those all up with the bottom here too. So x to the third would be, subtract that, all of those terms cancel out. So I end up with 0. Now when I'm choosing what I have to multiply by, I'm trying to get my first term that's not 0, so 2x squared, to match the first term of the divisor. The only way to do that would be to multiply by 1. So I'm going to multiply by positive 1. Subtracting, I notice that I get a remainder of 0, which is a good thing. That means that my divisor is a factor of the dividend. So we're going to take our dividend and write it in its factored form. Now, some of you more savvy mathematicians might have noticed that we could have factored this one by grouping. It has 4 terms, so parentheses would have matched. Yes, I get it, but we are working on long division here, so we did division. However, we will come to a point where you can make the decision on how to find all roots all by yourself. So if you had seen that right away, yeah, eventually we'll get to the point where you could just do that. I notice here that 2x squared minus 8, that's quadratic. I can solve that. I could use square roots if I want to, or I could continue factoring. I notice that if I factor that polynomial, has a GCF of 2, resulting in a difference of squares. If you look at our quotient, you should recognize it. Our quotient is a sum of cubes, where a is equal to x and b is equal to 1. If you remember my lesson from factoring, you'll recall that this trinomial, x squared minus x plus 1, is not a factorable trinomial. We actually have to use a quadratic formula there to solve, but we are in a position where we can find all roots of this polynomial. So let's write the ones that we know right away. If 2 is equal to 0, there's no x, that doesn't result in a root. If this one's equal to 0, those three are all really simple for us by now. The roots we start with here are -2, -1, and 2. I know because I have that degree of 5, I am looking for 5 roots. This quadratic needs to be solved using the quadratic formula, which always results in 2 roots, giving me my final 2 of 1 plus or minus I square roots of 3 over 2. One other thing to pay attention to here is if we were asked to factor, we would stop and we wouldn't find the roots. However, these directions, if we go back and read them, it says, if so, write the factored form of the polynomial and find all roots of the polynomial. So we had more directions. If we were just asked to factor, we wouldn't go forward and solve.